Okay. Hello. My work calls estimation of nonlinear DSGE models with moment-based methods. At the beginning, some motivation for nonlinear estimation of the models. First of all, most of the dynamic stochastic general equilibrium models are nonlinear. And what is important, when we use linear approximation, we eliminate all influence of uncertainty. And another one is that linear approximation eliminates all influence of asymmetrics. And the last one, important thing, that linear approximation make likelihood function much more flat. And the next one is some motivation for moment-based methods. First of all, likelihood methods likelihood methods need nonlinear filters, which are really computationally expensive. Moment-based methods are not so computationally expensive. Another thing that moment-based methods are more robust, and we work with approximation of the model, so robustness is important. And another detail is that moment-based methods like DSGE var are heavily used for linear estimation, but there is only few works which use them for nonlinear estimation of DSGE models. And the next is some motivation for non-simulation method. First of all, if we use some likelihood or score function which is simulation based, then it's equivalent that we have some random errors in this likelihood or score function. So if we have random errors, we can't use usual maximization algorithm, and we have to use some less efficient algorithms. Another point is that if we use Bayesian approach and we use MCMC, then inefficiency of the MCMC increase about, for example, of Peter Silva, it increased about 10 times. You need 10 times more draws and 10 times more likelihood calculations if you have some random errors in a likelihood function. So, what do we have, what approach for nonlinear estimation do we have now? The most famous one is the particle filter. It suggests that we generate some draws and compute it from one period to another, just generate from distribution and try to use it for computing likelihood function. This approach is very slow, but if you have enough draws, enough particles, it could produce very high quality. But there is another approach which is sigma point Kalman filters. They much faster. They doesn't use stochastic draw. They use some special points, and it allows to compute moments of the unobserved variables, and this filter is about 100 times faster and produce the same quality than that the particle filter. And there is another filter-based approach. It's a quadratic Kalman filter. It has another ideology, but it produces almost the same quality, a little bit better than central difference Kalman filter, and it's a little bit slower than a Kalman filter, but in general this approach are equivalent in terms of speed and accuracy. And what we have about moments-based approach? We have a simulated method of moments of Roy-Morse, but as it was reported by him, it is really slow. It requires about 30 seconds for calculation of the likelihood of the score function. And there is another approach which called instrumental variables, but it is very restrictive. It requires that all variables in the model should be observed, which is impossible in the medium scale models. It's not possible. We always have some unobserved variables. So what do we suggest? Nonlinear approximation second-order perturbation method produce the following solution of the rational expectational problem. We have state variables here, and we have dependence on second-order dependence, and we have some observed variables y. We could easily compute equation for moments for first and for second moments and second lag moments, but this equation can be solved easily. We have few problems here. First of all, for equation for a first order moment require knowledge of the second order moment. Equation for a second moment require knowledge of first, third and fourth moment. So we cannot solve it directly. There are two possible solutions. We could approximate higher ordered moments, or we could just drop them. If we approximate higher order moments, then our equation became nonlinear, and we cannot solve it analytically, and we could only use some numerical solution. Here we can see here how to approximate higher order moments with normal approximation. Here dependence of the third moment, third non-central moment is depend on the first moment non-central, and second central moment dispersion. It's a simple equation. It's matrix U is permutation matrix which change the order of the Kronecker product, and here equation for fourth moment, and the last one is equation for normal approximation of the fourth moment. If you know second, fourth central moment. If you know second central moment of the normal distribution, you could easily compute fourth order moment of the normal distribution. And we can solve equation directly, so we use a simple iteration approach. We just use linear approximation of moments at the first step, and after that we recompute moments iteratively according to this formula, where here is a fourth moment which could be, we have two ways of solution. One is normal approximation of that, and another one is zero approximation, just dropping of this fourth moment. And we have some approximation of moment, of nonlinear model moments. We need some estimation of the quality of this approximation and corresponding estimation approach. First of all, first approach is quality check approach. We estimate a simple DSGE model with asset prices. We simulate it 100,000 observation 10 times. We compute mean and standard deviation of these moments, and also we compute moments with our approach. Normal approximation of higher than second moment, normal approximation with higher than zero approximation with higher than second moment, and zero approximation with higher than third moment. And we compute root mean square error of this moment. This first approach of quality checking. The second one is we use the same simple model. We estimate it. We generate 400 observation from this model. We estimate parameters and repeat this 100 times. And after that, we could compute root mean square errors of parameter estimation. And why we don't use Bayesian approach for estimation? We use maximum likelihood and generalized method of moments and indirect inference. If we try to use Bayesian, we need at least about 20,000 rows, which with the speed of the central difference Kalman fit require about 22 hours for estimation, for one estimation, and if we need 100 estimation for computing of root mean square error, we would need about 90 days. And if we use simple maximum likelihood approach, we need about only 2 hours for estimation, and which means only 9 days for computing of root mean square of estimation. So, what is the model which we use for estimation? It's really simple. We have householders who maximize its utility function. It has budget restriction. It consumes it by bonds, stocks, and it have income from previous both bonds, stocks, and it have some exogenous income. The letter Z means that it's exogenous process, which are autoregressive process. We just move to the stable variables, make transformation. We have optimal condition. We add here some additional exogenous process, which mean that our agents have boundary rationality, and we have some balance restriction, which means that dividend growth is exogenous, the amount of bonds is exogenous, and amount of stocks is equal to 1. And all exogenous processes are after regressive processes. So, what do we have after estimation of the moment of the models? We see that if we use zero approximation of the higher moments, then errors after the first iteration, errors are really high. But after the second, it became much smaller, and after the 5th iteration, the errors of our approach is smaller than of simulation of 100,000 observation. You see that standard deviation is about 0-4, and we have 0-5. And here the sum of root mean square errors, and with a zero approximation, we have sum of root mean square error about 0-4. And if we use normal approximation, we see that the picture is almost the same, but we see that the quality became much better. It's about 0-5 instead of 0-4. And we see this, the same picture here, that after the first iteration we have high errors, after the second we have much smaller, and the difference of errors between 5 and 10 iteration isn't really high. Also, we compute for the case of zero approximation of higher than third moment, and here the picture is almost the same as for approximation of the normal approximation of higher than second moment, but computational time for zero approximation higher than third moment is much higher. This approach is slower than previous one, so we don't use it for estimation purpose. And here some words about our estimation approach. One of our estimation approach, it's about indirect inference. With indirect inference, we know that the data generating process is a result of a second order perturbation approach, and indirect inference said that we don't maximize the likelihood of the data, but we maximize likelihood or quasi-likelihood of the moments which depend on the data. In case of our model, we use DSGE approach, at this approach we maximize likelihood of the VAR, where its parameter depend on the model parameter theta. And here are results of the estimation of parameters. We can see that time of our approach is much smaller. The central difference Kalman filter requires about 4 seconds for one likelihood calculation. And our approach requires less than 1 second with normal approximation and about 4 times smaller for a zero approximation. If we look at the sum of root mean square error of parameters estimation, we see that normal approximation and 10 iteration is produce the best quality of estimation. The second one is the case of 0 approximation and 5 iteration. This case is not really reliable because when you compute 0 approximation, it is sometimes that covariance matrix is not positive defined, so it cannot compute a likelihood function, and we use true value of parameters as initial for maximization. So at many cases, about a half of cases, 0 approximation with 5 iteration does not move from initial point. So this is not really reliable results. But if we see on other part of our table, we can see that if we use other measure of the quality, then as sum of mean square error, then the best one is 0 approximation with 10 iteration, and the second one is a central difference Kalman filter. And our normal approximation is really close, but it's third one. So we also compute some results with generalized method of moments, and we can see that with generalized method of moments, the errors are much higher. So it's predictable result that indirect inference is much more efficient than GMM. So what do we have? We have 2 approaches for nonlinear estimation of DSGE models, and one of them is faster, 9 times faster than the best known before approach, central difference Kalman filter, and another one is about 30 times faster. And if we try to use GMM, it doesn't produce high quality estimation, but if we use indirect inference, we have almost the same quality as the central difference Kalman filter, but much faster. Thank you for your attention. If you have some question, I will try to answer.
Well, you mentioned some numbers like 22 hours, 90 days. Are these numbers correspond to the simple laptop?
Yes, it's maybe these numbers for my home PC, which may be a little bit more efficient, a little bit better than usual laptop, but not really big difference.
But there will be difference if we use big servers.
Of course, supercomputer could produce it much faster, but here example of really small model. If you try to use it with some DSGE medium scale model, it's here we have about 11 state variables and 70 variables in the model. If you use medium scale model, your time would be much higher. For example, if you use about 20 variables, state variables, 2 times higher, then central difference Kalman filter would require about 10 seconds for one likelihood calculation. And our approach would be about 1 second, depending on which one do you use, normal or zero approximation. So it's this difference very important when you try to use nonlinear estimation for medium or large scale models, even if you use supercomputer or something like this. Yep.
When you mentioned EG one approach, you mentioned the shortcuts, it is something new, because when I studied EG models, DG1 was something that was proposed by shortcut.
Yeah, there is a small. The difference is, but it is small because here the main difference is that we have. This dependence is different because if we use usual DSGE approach, there is dependence between. We compute moments and we compute moments from linear approximation of the model and compute from that parameters of the VAR. But here we use second order approximation and we have different moments, and as a result we have different parameters of VAR. So there is different in techniques but not in approach.